Voyager 2 is dying. Not quickly, not dramatically, not in any way that will produce a visible event or a detectable signal to any instrument anywhere. It is dying the way all machines die when left long enough without maintenance in environments they were not designed to survive indefinitely, through the gradual, irreversible depletion of the energy source that keeps it functioning. Its radioisotope thermoelectric generators, the RTGs, that have been converting the heat of decaying plutonium-238 into electricity since the spacecraft launched in August 1977, are producing less power every year. The decay of plutonium-238 follows an exponential curve with a half-life of 87.7 years. Every year, the power output drops by approximately 4 watts. The total power available to the spacecraft was approximately 470 watts at launch. It is approximately 250 watts now. By the early 2030s, it will fall below the threshold required to keep even the last active scientific instrument operating. When that happens, Voyager 2 will go silent. Not suddenly. The transition from functioning to non-functioning will be managed gradually by the mission team at JPL, who will continue making decisions about which instruments to shut down to keep others running, extracting the last possible data from the last possible instrument, until the power finally falls below what is needed. And then, the signal from Voyager 2, the faint whisper of 23 watts, transmitted across the billions of kilometers of interplanetary and now interstellar space, will stop. After that, Voyager 2 will continue. That is the thing about this particular death that is unlike most deaths. The spacecraft will stop transmitting. It will stop measuring. It will stop doing any of the things that make it scientifically useful. But it will not stop moving. The laws of physics that have governed its trajectory since launch, Newton's laws of motion modified by the gravitational fields of every body it has passed, will continue to govern it. No friction in the vacuum of space, no force acting to slow it. Voyager 2, at the moment of its final silence, will be moving at approximately 15.4 kilometers per second relative to the Sun, and it will continue at that velocity essentially forever, unless it hits something, which, in the vastness of interstellar space, is extraordinarily unlikely. Tonight we are going to trace the final journey of Voyager 2. Not the journey that has already happened, the astonishing 47-year traversal of the solar system from Earth to the outer planets to the edge of the heliosphere and beyond, but the journey that is still to come, the journey after silence, the trajectory through interstellar space that will unfold over thousands and millions and billions of years after the last signal has been sent and received. And we are going to talk about one specific destination, the last significant astronomical encounter that Voyager 2 will have on any timescale that can be meaningfully described. Not a planetary flyby, not a stellar encounter, something stranger and more distant and in some ways more poignant than either. Before we begin, if you put this on because the night is long and you need something to settle into, stay. What follows is the longest voyage story ever told about a real object. Let us start with where Voyager 2 is right now, because understanding its current position and trajectory is essential for understanding where it is going. As of 2025, Voyager 2 is approximately 133 astronomical units from the Sun, approximately 133 times the Earth-Sun distance, or roughly 20 billion kilometers. It crossed the heliopause, the boundary between the heliosphere and interstellar space, in November 2018 at approximately 119 astronomical units. Since that crossing, it has been in interstellar space, in the region between the stars, bathed in the interstellar plasma and magnetic field rather than the solar wind. It is moving away from the Sun at approximately 15.4 kilometers per second, or about 3.2 astronomical units per year. This is slightly slower than Voyager 1, which is moving at approximately 17 kilometers per second in a different direction. The difference in speed reflects the different trajectory each spacecraft took after leaving the planetary system. Voyager 1 received a gravitational assist from Saturn that put it on a faster trajectory out of the solar system, while Voyager 2 continued to Uranus and Neptune before departing. The direction Voyager 2 is travelling, the direction it is heading into interstellar space, is approximately toward the constellation Telescopium in the southern celestial hemisphere. This is the direction in which it will travel essentially indefinitely, modified only by the tiny gravitational perturbations it receives from stars it passes near, which will gradually accumulate over millions of years to produce unpredictable changes in its trajectory. Voyager 2's scientific instruments, the ones still operating, are measuring the interstellar medium. The Plasma Wave Science instrument is measuring the density and oscillation frequency of the interstellar plasma. The magnetometer is measuring the interstellar magnetic field. The low-energy charged particle instrument and the cosmic ray subsystem are measuring the flux and energy spectrum of galactic cosmic rays. Together, these instruments are providing the first direct in situ measurements of the local interstellar medium from the southern direction, complementing the measurements Voyager 1 has been making from the northern direction since 2012. The two Voyagers are therefore providing a stereo view of the local interstellar medium, measuring properties of the interstellar plasma and magnetic field from two different directions simultaneously, allowing scientists to distinguish between properties that are locally uniform and properties that vary with direction. This stereo capability, made possible by the fact that the two spacecraft were sent on different trajectories that carried them in different directions out of the solar system, is scientifically valuable in ways that a single spacecraft could not provide. But the power is declining. The instruments will go silent, and then Voyager 2 will travel on. Let us talk about what interstellar space is like, the specific physical environment through which Voyager 2 is currently travelling and will continue to travel for the foreseeable future. The interstellar medium, the matter filling the space between stars, is not empty. It contains gas, dust, cosmic rays, and magnetic fields distributed in complex and varied ways. The average density of the interstellar medium is approximately 1 atom per cubic centimetre, compared to approximately 10 to the 19 molecules per cubic centimetre in Earth's atmosphere at sea level. This is an extremely low density, far lower than the best vacuum achievable in any laboratory on Earth, but not zero. The composition of the interstellar medium is approximately 70% hydrogen, 28% helium, and 2% heavier elements, reflecting the overall composition of the universe with contributions from the nuclear synthesis that occurred during the Big Bang and in stellar interiors over the history of the galaxy. The interstellar medium is not uniform. It exists in several distinct phases at very different temperatures and densities. The hot, ionized medium, plasma heated to temperatures of 10,000 to 1 million Kelvin by supernova shockwaves and other energetic events, fills a large fraction of the volume of the galaxy. The warm, neutral medium gas at temperatures of approximately 6,000 to 10,000 Kelvin in neutral form, forms clouds and filaments. The cold neutral medium, dense clouds of neutral gas at temperatures of 50 to 100 Kelvin, is where stars form. Our solar system is currently moving through a specific region of the interstellar medium called the local interstellar cloud, a region of warm, partially ionized gas at approximately 6,000 Kelvin, with a density of about 0.3 atoms per cubic centimetre. This is somewhat denser and warmer than average for the interstellar medium. The local interstellar cloud is itself embedded in a larger structure called the local bubble, a region of the galaxy approximately 300 light-years across, where the interstellar medium has been swept out by supernova explosions that occurred approximately 10 to 20 million years ago, leaving a cavity of hot, low-density plasma. Voyager 2 is moving through the local interstellar cloud right now. Its instruments are measuring the specific properties of this cloud, the density, temperature, ionization state, and magnetic field of the specific region of interstellar space immediately surrounding our solar system. This is information that no other instrument can provide, not telescopes observing the interstellar medium from afar, not theoretical models predicting its properties. Voyager 2 is there. After the instruments go silent, Voyager 2 will continue through the local interstellar cloud. How long it will remain in this cloud depends on the cloud's extent and the spacecraft's trajectory through it. Current estimates suggest the solar system will exit the local interstellar cloud somewhere between now and approximately 20,000 years in the future. The boundary is not precisely determined because the cloud's shape and extent are not precisely known. Voyager 2, moving at 3.2 astronomical units per year, will cover significant distance through the cloud during this time, but the cloud is large enough that it will take thousands of years to traverse. Let us now talk about the first significant astronomical encounter in Voyager 2's future, its closest approach to another star system. Voyager 2 is heading in the approximate direction of the constellation Telescopium. It is not heading directly toward any known star. It is heading into the relatively empty space between stellar systems, which is the typical condition of interstellar space. The nearest star system to the Sun, Alpha Centauri and its companion Proxima Centauri, is in the direction of the constellation Centaurus, roughly perpendicular to Voyager 2's direction of travel. Voyager 2 is not heading toward Alpha Centauri. The closest approach of Voyager 2 to any known star in the foreseeable future is predicted to occur in approximately 40,000 years. At that time, Voyager 2 will pass within approximately 1.7 light-years of a red dwarf star called Ross 248, a small dim star in the constellation Andromeda, approximately 10.3 light-years from Earth today. Ross 248 is an M-type red dwarf with a mass of approximately 0.136 solar masses and a luminosity of approximately 0.0018 times that of the Sun. It is intrinsically extremely faint, visible only through a telescope from Earth. In 40,000 years, it will have moved through space enough, because all stars move relative to each other, that it will be only about 3 light-years from Earth at closest approach to our solar system, briefly becoming the closest star to the Sun before moving away again. At the time of Voyager 2's closest approach to Ross 248, the spacecraft will be approximately 1.7 light-years from the star, roughly 0.5 parsecs. This is a significant fraction of the current distance to the nearest star, but it is not a close encounter in any practical sense. Voyager 2 will not be captured by Ross 248's gravity. The approach velocity is far too high relative to the weak gravitational field of this small star. It will simply pass at this distance, continuing on its trajectory, slightly deflected by the gravitational influence of Ross 248 by an amount too small to be easily calculated without precise knowledge of the approach geometry. From the perspective of Voyager 2 at this closest approach, 40,000 years from now, Ross 248 will appear as a bright star in the sky. Not the brightest object visible. The Sun will still be visible, much dimmer at the increased distance, but still the source from which Voyager originated. Ross 248, at 1.7 light-years, will appear somewhat brighter than the current brightness of Alpha Centauri, as seen from Earth. A significant but not overwhelmingly bright star. But Voyager 2's instruments will long since have fallen silent. No one and nothing on Voyager 2 will observe this encounter. The closest stellar passage in Voyager 2's entire foreseeable trajectory will happen in complete silence. The spacecraft moving through space without measuring, without transmitting, without any activity that distinguishes it from a simple lump of metal moving through the void. The golden record it carries will be there. The sounds of Earth, the thunder, the waves, the music, the languages, the laughter, will be encoded on its surface, physically present, preserved in the metal. But there will be no power to play it, and no one to hear it. Let us now talk about the trajectory of Voyager 2 over longer timescales, over tens and hundreds of thousands and millions of years, and what it tells us about the fundamental isolation of stars from each other. After the Ross 248 encounter, approximately 40,000 years from now, Voyager 2 will continue into the depths of interstellar space. There are no other close stellar encounters predicted for hundreds of thousands of years after the Ross 248 passage. Voyager 2 will travel through the interstellar medium, through the local interstellar cloud, then through whatever region of the local bubble it encounters next, then possibly into a denser interstellar cloud, without coming close to any star. This long, empty transit illustrates one of the most fundamental facts about the galaxy. Stars are extraordinarily far apart. The average distance between stars in our region of the Milky Way is approximately 4 to 5 light-years. Voyager 2, moving at 15.4 kilometers per second, would take approximately 80,000 years to travel 4 light-years. 4 light-years being roughly the distance to the nearest star. The universe has been around for approximately 13.8 billion years, long enough for Voyager 2 to have made approximately 170,000 such trips across 4 light-year distances. But the chance of encountering a star in any random direction of travel remains low, because stars are so tiny relative to the distances between them. The cross-section of a star, the area a target would need to have to intercept Voyager 2 travelling in a given direction, is tiny compared to the area of a sphere of radius 4 light-years centred on the Sun. A star the size of the Sun has a radius of approximately 700,000 kilometres. A sphere of radius 4 light-years has a radius of approximately 38 quadrillion kilometres. The ratio of these areas is approximately 10 to the negative 22, meaning that if stars were randomly distributed, there would be roughly a 1 in 10 to the 22 chance of hitting one while travelling 4 light-years in a random direction. Stars are not randomly distributed. They are clustered in the galactic disk, and the probability of an encounter is not quite this low. but the calculation illustrates the fundamental emptiness of interstellar space. Voyager 2 will travel between the stars for an enormous amount of time without encountering anything significant. Over millions of years, the cumulative gravitational perturbations from stars passing near Voyager 2's trajectory, even stars that come no closer than a light year or two, will gradually modify the spacecraft's trajectory in ways that become impossible to predict. This is the phenomenon of gravitational chaos in orbital mechanics. Small perturbations accumulating over time into large, unpredictable deviations. Within approximately 10 million years, the specific trajectory of Voyager 2 becomes unpredictable from any information we have today about the positions and velocities of nearby stars. This is the timescale at which Voyager 2's future becomes fundamentally unknowable from our current knowledge. We can predict its trajectory for tens of thousands of years with good accuracy. We can make probabilistic statements about the likelihood of stellar encounters over millions of years. Beyond that, beyond the horizon of gravitational predictability, Voyager 2's trajectory is indeterminate. It could encounter another star. It could be captured into orbit around a stellar system. It could continue wandering indefinitely through interstellar space. Let us now talk about what Voyager 2 carries with it, about the Golden Record, and what it means for this spacecraft to be an emissary from Earth into interstellar space. Like Voyager 1, Voyager 2 carries a Golden Record, a gold-plated copper disc 12 inches in diameter, encoded with sounds and images from Earth. The record was assembled under the direction of Carl Sagan and contains 116 images encoded as analog signals, greetings in 55 languages, sounds of Earth, surf, wind, thunder, birds, whales, a baby crying, a mother's first words to her child, and 90 minutes of music ranging from Bach to Chuck Berry to traditional music from dozens of cultures. The record also carries instructions for playback, encoded in binary on the record's cover, along with a diagram of the solar system showing the spacecraft's origin, and a stylus for playing it. The instructions assume that any civilization finding the record can decode binary information and can construct a playback device. Assumptions that are not obviously correct for any conceivable finder, but that represent the most reasonable approach available. The probability that the Golden Record will ever be found and decoded by any extraterrestrial civilization is vanishingly small. The record is tiny, a 30-centimeter disk, and space is vast. Even with perfect knowledge of Voyager 2's trajectory, it would take a civilization with technology far beyond our own to intercept a specific small object moving through interstellar space. The record was not created with a realistic expectation of recovery. It was created as a statement, as a physical manifestation of the choice to send something of ourselves along with the first human-made objects to leave the solar system. Carl Sagan described the Golden Record as a message in a bottle cast into the cosmic ocean. The bottle will drift essentially forever. The cosmic ocean is vast beyond comprehension. The chance of the bottle being found is negligible. But the act of putting the message in the bottle, of deciding that this is what we want to say about ourselves if anyone is ever listening, is itself meaningful. What is on the record reflects a specific set of choices made by a specific group of people in 1977 about what is essential about humanity. Those choices are imperfect. The 1977 committee made decisions that people today would make differently. But the imperfection is itself human. The record is a document of 1977 humanity attempting to represent all of humanity, knowing it could not succeed completely, making the attempt anyway. The record will outlast everything else associated with the Voyager mission. It will outlast the mission team. It will outlast JPL. It will outlast NASA. It will outlast the United States. It will outlast human civilization in whatever form that civilization takes. Calculations of the record's longevity in interstellar space, exposed to cosmic rays, micrometeorite impacts, and the sparse plasma of the interstellar medium, give figures of approximately 1 billion years before significant degradation. The record will survive for 1 billion years. The Sun will expand into a red giant in approximately 5 billion years. The Earth will be uninhabitable, possibly engulfed, before then. Whatever is left of human civilization in billions of years will not be recognizable as what we are today. But Voyager 2 will still be out there. The golden record will still be attached to it. The sounds of Earth encoded on its surface will still be physically present, waiting to be played, carrying the voice of a child saying hello from the children of planet Earth. Let us now talk about what happens to Voyager 2 on the longest timescales, on the timescale of the galaxy itself. The Milky Way galaxy is approximately 100,000 light-years in diameter. Voyager 2, moving at 15.4 kilometers per second, would take approximately 2 billion years to travel 100,000 light-years, ignoring the gravitational influences that would dramatically modify its trajectory over such timescales. In 2 billion years, the Earth will likely still exist, but will be increasingly inhospitable as the brightening sun drives the runaway greenhouse effect. In 5 billion years, the sun will have left the main sequence. In approximately 4.5 billion years, the Milky Way will have merged with the Andromeda galaxy, a process that will take hundreds of millions of years and will dramatically restructure the orbits of stars throughout both galaxies. The merger of the Milky Way and Andromeda will not be the violent collision it sounds like. Stars are so widely separated that the actual collision of individual stars during the merger is extremely unlikely. But the gravitational dynamics of the merger will significantly perturb the orbits of stars throughout both galaxies, and will generate tidal streams and shells of stars ejected to large distances. Voyager 2, if it has not been significantly perturbed already by then, could be affected by the gravitational dynamics of the merger. But calculating specifically what would happen to it on this timescale is impossible with current knowledge. On timescales of hundreds of billions of years, the galaxy will have substantially exhausted its supply of gas available for star formation. The current stellar population will have aged. Most stars, more massive than the Sun, will have completed their lives and left behind white dwarfs, neutron stars, or black holes. The galaxy will be dimming. Voyager 2 will still be moving through it, now through an increasingly dark and depopulated galaxy, still carrying the golden record. On timescales of trillions of years, stellar interactions will gradually eject most stars from the galaxy through a process called dynamical relaxation. Close encounters between stars transferring energy from some to others in a random walk that eventually sends stars to very high velocities and allows them to escape the galaxy's gravity. The same process might eventually eject Voyager 2 from the merged Milky Way Andromeda galaxy entirely, sending it into the intergalactic void. On timescales of 10 to the 20 years, 100 billion years, stellar interactions will have stripped the galaxy of most of its stars. The merged galaxy will consist primarily of stellar remnants, white dwarfs slowly cooling to black dwarfs, neutron stars, and black holes. These remnants will in turn be slowly ejected or drawn into the central supermassive black hole through continued dynamical relaxation. On timescales of 10 to the 40 years, if current theoretical models are correct, protons will decay. The spacecraft material, the aluminium structure, the electronic components, the golden record, will have slowly decomposed as its constituent protons decayed into lighter particles. Voyager 2 as a physical object will have ceased to exist. The information it carries, the sounds of Earth encoded on the record, will have been converted to radiation and lighter particles. After 10 to the 40 years, there will be nothing left of Voyager 2 in any physical sense. But the gravitational waves it produced by its motion through space, infinitesimally weak, produced by its tiny mass moving at non-relativistic velocities, will have propagated outward at the speed of light in every direction. By the time proton decay has erased the spacecraft, the gravitational waves from its first seconds of motion will have travelled approximately 10 to the 32 light-years from their origin, a distance that dwarfs the observable universe. These gravitational waves will continue propagating essentially forever. They are solutions to the wave equation in a universe that in the relevant era may no longer contain matter to interact with them in any significant way. They will be the last physical trace of Voyager 2 and of the civilization that built it, propagating through the structure of space-time in the darkening universe long after everything else is gone. This is the true final destination of Voyager 2, not Ross 248, not the outer reaches of the Milky Way, not even the intergalactic void, but the structure of space-time itself, the ripples it made simply by existing and moving, propagating outward at the speed of light into a universe that will have fundamentally changed around them. Let us now talk about something that is often overlooked in discussions of the Voyager mission, the specific human story of the people who built Voyager 2 and who have spent decades maintaining contact with it. Voyager 2 was launched on August 20th, 1977, 16 days before Voyager 1. The order of launch was reversed from the order of naming. Voyager 2 was actually launched first, but Voyager 1 was given its name because it was on the faster trajectory that would carry it past Jupiter and Saturn before Voyager 2. The people who built Voyager 2 are now in their 70s, 80s and 90s, those who are still alive. Many of the engineers and scientists who designed the spacecraft, worked its early mission, and made the decisions that determined its trajectory are no longer alive. The mission has outlived many of those who created it. The current Voyager mission team is a small group, a few dozen people at the Jet Propulsion Laboratory in Pasadena, California, who monitor the spacecraft, maintain contact, interpret the data, and make decisions about which instruments to keep running as power declines. These are people who have chosen to spend significant portions of their careers on a mission launched before most of them were born, maintaining contact with spacecraft that are now the most distant human-made objects in existence. In 2023, Voyager 1 experienced a fault in its flight data system that caused it to transmit unreadable data. The mission team spent months diagnosing the problem through the 22.5-hour round-trip communication delay, sending commands, waiting nearly a day for responses, analysing the replies, sending new commands. They identified a specific chip in the flight data system that had failed, a chip that stored a portion of the code used to format data for transmission. They then developed a solution, relocating the affected code to a different part of the memory, and successfully implemented it over the same 22.5-hour delay. A spacecraft 24 billion kilometers away with hardware from the 1970s was reprogrammed through a 45-hour conversation conducted at the speed of light. Voyager 2 similarly requires continuous attention. Its systems are aging, its power is declining. Decisions about instrument shutdowns must be made carefully. Each decision is irreversible, each instrument shutdown permanent. The team must balance the scientific value of different instruments against the power requirements of keeping them running, and the risk that declining power will cause failures if systems are not managed proactively. This ongoing work, the daily monitoring of telemetry, the analysis of data, the careful management of a failing spacecraft, is done by people who know they are the last generation who will maintain contact with these spacecraft. The people currently working on the Voyager mission are the last people who will ever communicate with Voyager 2. When they retire, or when the mission ends, whoever comes after them will inherit only the record of what was learned, not the ability to ask new questions. This gives the current Voyager mission a specific quality, a sense of final opportunity, of extracting the last possible scientific value from instruments that cannot be repaired or replaced. Every measurement taken by Voyager 2's instruments while they still function is a measurement that cannot be made by any other means. The direct, in situ measurement of the interstellar medium from a spacecraft traveling through it is irreplaceable. No telescope observation from within the heliosphere can substitute for it. The team knows this. It shapes how they approach each day of the mission, the awareness that the data coming back is unique and finite, that the opportunity to gather it is closing, that what they are doing represents the last chapter of one of the most scientifically productive missions in the history of space exploration. Let us now talk about what comes after Voyager 2, about whether any future mission will follow it into interstellar space, and what such a mission might look like. Voyager 2 reached the heliopause, the boundary of interstellar space, after approximately 41 years of travel. This is extraordinarily long by any human timescale. No mission currently under development would take this long. The engineering, financial, and institutional challenges of sustaining a mission for 40 years, while technology, politics, and organizational priorities change, are enormous. But proposals have been made for an intentional interstellar precursor mission, a spacecraft specifically designed to reach interstellar space faster than Voyager, and to carry more capable instruments for measuring the interstellar medium. The most developed of these proposals is the interstellar probe concept, studied by a team at the Johns Hopkins University Applied Physics Laboratory under the direction of Ralph McNutt. The interstellar probe concept proposes launching a spacecraft with a Jupiter gravity assist to achieve speeds significantly higher than Voyager's, perhaps 7 to 10 astronomical units per year, compared to Voyager 2's 3.2. At this speed, the probe could reach the heliopause in approximately 15 to 20 years, a mission timescale comparable to other long-duration flagship missions. It would carry a comprehensive suite of instruments specifically designed for characterizing the interstellar medium and the heliospheric boundary in detail that the Voyager instruments, designed primarily for planetary science and only incidentally for interstellar work, cannot achieve. The interstellar probe concept was studied in detail in 2019 to 2021 in preparation for the Planetary Science Decadal Survey. The study concluded that such a mission was technically feasible with near-term technology and scientifically extremely valuable, providing measurements of the interstellar medium, the heliospheric structure, and the cosmic background that no other type of mission could achieve. The Decadal Survey recognized the scientific value of the concept, but did not recommend it as a funded priority in the current decade, citing cost and the availability of other priorities. Whether such a mission will be developed in the coming decades remains to be determined. The scientific case is strong. The Voyager data has revealed that the interstellar medium and heliospheric boundary are more complex than expected, and a dedicated mission could characterize them in dramatically more detail. But the institutional and financial challenges are significant. In the meantime, Voyager 2 continues, declining in power, sending back data, making measurements that no other instrument can make, being listened to by a small, dedicated team who know they are among the last people who will ever hear from it. And moving at 15.4 kilometers per second away from the Sun, through the interstellar medium, toward Ross 248 and the unimaginable future that lies beyond it. Let us now talk about what Voyager 2's data has already told us about the interstellar medium, about the specific discoveries made since it crossed the heliopause in 2018 that were not anticipated and that are still being understood. When Voyager 2 crossed the heliopause in November 2018, the crossing was sharp, sharper than most models predicted. The transition from heliospheric to interstellar plasma happened over a period of approximately 1 day, as Voyager 2 moved approximately 1.5 astronomical units. This sharpness suggests that the heliopause is a well-defined boundary, a thin layer separating the two plasma regimes, rather than a gradual transition zone. The magnetic field at the heliopause did not change direction as much as expected. Inside the heliosphere, the magnetic field direction is determined by the direction of the interplanetary magnetic field, itself determined by the Sun's rotation and the geometry of the solar wind. Outside the heliosphere, the field direction should be determined by the local interstellar magnetic field, which models predicted would be oriented differently. But Voyager 2 found that the field direction changed only slightly at the crossing. The interstellar magnetic field in the vicinity of the heliopause appears to be approximately aligned with the heliospheric field, rather than dramatically different from it. This was not expected. It has implications for understanding the large-scale structure of the local interstellar magnetic field and its relationship to the heliosphere. The alignment may be coincidental. The local interstellar field just happens to be oriented similarly to the average heliospheric field in the direction Voyager 2 crossed. Or it may reflect a physical interaction. The heliosphere may have distorted the local interstellar field into approximate alignment near the boundary. Distinguishing these possibilities requires measurements from more crossing points, which is not possible with only 2 spacecraft. Voyager 2 also detected a thin, hot layer of plasma at the heliopause, sometimes called the hot mantle, that was warmer than either the heliospheric plasma outside the termination shock or the interstellar plasma outside the heliopause. This hot layer is approximately 10 to 20 astronomical units thick and has a temperature of several 100,000 Kelvin, significantly hotter than the adjacent regions. Its origin is not fully understood. One proposed mechanism involves the acceleration of interstellar neutral atoms that cross the heliopause, a process called pickup ion formation, which can create energetic particles that heat the local plasma. The plasma density outside the heliopause, in the interstellar medium, was measured by Voyager 2's plasma wave instrument and found to be approximately 0.055 electrons per cubic centimetre. This is consistent with previous estimates of the local interstellar cloud density based on indirect observations, but represents the first direct measurement of this quantity from outside the heliosphere in the direction Voyager 2 travelled. Voyager 2 also measured the cosmic ray flux outside the heliopause and found, as expected, that it is higher than inside. The heliosphere acts as a partial shield against galactic cosmic rays, and the flux increase upon crossing the heliopause confirms this. But the increase was not as dramatic as some models predicted. The heliospheric shielding of cosmic rays is somewhat less effective than those models assumed. All of these specific findings, the sharp heliopause crossing, the magnetic field alignment, the hot mantle, the plasma density, the cosmic ray flux, are pieces of a picture of the heliospheric boundary that is more complex than the models that preceded direct measurement. The data is still being analysed. Papers are still being written, the understanding is still evolving. This is what Voyager 2 is doing right now, making measurements, sending data, advancing human knowledge of the space immediately surrounding our solar system in ways that no other instrument can. And every day, the power drops a little more. The time remaining is measured in years, not decades, not centuries, but years. Let us now talk about the specific moment that will end the mission, about what the final days of Voyager 2's active life will look like and what will be left afterward. The Voyager mission team has been managing the power decline for years, shutting down heater systems, science instruments, and other subsystems one by one as the available power has decreased. Each shutdown is permanent. The heater, keeping a specific instrument warm against the cold of space, is turned off, and that instrument freezes, its electronics damaged beyond recovery, its scientific contribution ended. Currently, Voyager 2 has 4 active science instruments: the Plasma Wave Science System, the Magnetometer, the Low Energy Charged Particle Instrument, and the Cosmic Ray Subsystem. The mission team is working to keep all 4 operating as long as possible, balancing the power requirements against the declining supply. As power drops further, the team will face increasingly difficult decisions. Which instrument to sacrifice to keep others running? Which measurements are most valuable in the remaining time? The Plasma Wave Science System is probably the most scientifically valuable of the remaining instruments for the interstellar mission. It measures the plasma density and wave activity in the interstellar medium directly, and has produced some of the most significant findings from the post-heliopause portion of the mission. The magnetometer provides direct measurement of the interstellar magnetic field. The particle instruments characterize the cosmic ray and energetic particle environment. Each of these measurements is unique. No other instrument in any other location is measuring these properties of the interstellar medium directly. Every day that these instruments continue to function is a day of scientifically irreplaceable data. The end will not be sudden. As the last instrument's power falls below threshold, the instrument will cease to function. The spacecraft's computers and radio transmitter may continue operating for a time, sending engineering telemetry about the spacecraft's status even after the science instruments have gone silent. Eventually, even the transmitter will lack sufficient power, and the signal from Voyager 2 will stop. The antennas of the Deep Space Network, the 70-metre dishes at Goldstone in California, Canberra in Australia, and Madrid in Spain will continue to point in the direction of Voyager 2 for a time. They will receive nothing. The noise floor of the receivers, the thermal and quantum noise that limits sensitivity, will produce a background signal, but the specific 8.4 GHz carrier frequency of Voyager 2's transmitter will no longer be detectable above the noise. After a period of verification, confirming that the absence of signal is genuine rather than a communication anomaly, the mission will be formally declared over. The last entry in the Voyager 2 mission log will be made. The tracking antennas will be redirected to other targets. The small mission team will disperse, to retirement, to other missions, to the record of what they achieved. And Voyager 2 will continue, in silence, moving at 15.4 kilometers per second, with the golden record still attached, with the sounds of Earth still encoded on its surface. Moving away from the sun that made it, and the Earth that built it, and the civilization that sent it out. 40,000 years from now, it will be near Ross 248, then farther still. Through the interstellar medium, through the slow evolution of the galaxy, carrying its message from a moment in time that by then will be incomprehensibly remote, a moment before the permanent human presence in space that will by then either exist or not exist, a moment before whatever happens to the civilization that right now is listening to the last signals from its most distant emissary. Voyager 2 is dying. It will be silent soon, and it will keep moving forever. Let us talk about what the trajectory of Voyager 2 tells us about the specific geometry of our solar system's position in the galaxy, and why the direction Voyager 2 is traveling reveals something about the structure of the space immediately surrounding us. The two Voyager spacecraft were sent in different directions, not by accident, but as a consequence of the planetary alignment that made the Grand Tour possible. The Grand Tour trajectory, which exploited a rare alignment of the outer planets that occurs approximately once every 175 years, required Voyager 1 to fly past Jupiter and Saturn, and then be deflected by Saturn's gravity into a trajectory that carried it roughly northward out of the ecliptic plane. Voyager 2 flew past Jupiter, Saturn, Uranus and Neptune, and was deflected by Neptune's gravity into a trajectory that carried it roughly southward. The result is that the two Voyagers are exploring different directions of interstellar space simultaneously. Voyager 1 probing the interstellar medium in the direction of the constellation Ophiuchus in the northern celestial hemisphere, Voyager 2 probing it in the direction of Telescopium in the southern hemisphere. These two directions are approximately on opposite sides of the sky relative to the ecliptic plane, giving a north-south stereo view of the heliospheric boundary and the local interstellar medium. This geometric complementarity has scientific value beyond what either spacecraft could provide alone. The heliosphere is not a perfect sphere. It is deformed by the ram pressure of the solar wind against the flow of the local interstellar medium. The Sun is moving through the local interstellar medium at approximately 26 kilometers per second in the direction of the constellation Lyra, the so-called apex of the Sun's way. This motion compresses the upwind heliosphere, the side facing the direction of travel, and stretches the downwind heliosphere, the side facing away. Voyager 1 crossed the heliopause at approximately 121 astronomical units. Voyager 2 crossed it at approximately 119 astronomical units, slightly closer despite travelling in a different direction. This small difference contains information about the shape of the heliosphere specifically about whether the asymmetry between the directions the two spacecraft travelled reflects the expected compression from the interstellar medium flow, or something more complex. The crossing distances of 121 and 119 astronomical units are closer to each other than many pre-mission models predicted. Some models anticipated more significant asymmetry, with the upwind heliosphere considerably smaller than the downwind heliosphere. The relative similarity of the crossing distances for the two voyages suggests either that the true asymmetry is smaller than these models predicted, or that the specific directions the two spacecraft travelled happened to sample regions of similar heliospheric radius, despite the overall asymmetry. Resolving this question requires either more spacecraft crossing the heliosphere in other directions, which is not going to happen in the near term, or improving our theoretical models of heliospheric dynamics to the point where they can fit the observations from the two existing crossings. This is an active area of computational heliophysics, where numerical simulations of the heliosphere are progressively improving in resolution and physical sophistication. The specific direction Voyager 2 is travelling, toward telescopium, is in the general downwind direction relative to the motion of the solar system through the interstellar medium. Downwind is the direction from which the interstellar medium is flowing toward the Sun. A downwind crossing might be expected to encounter a larger heliopause distance. The interstellar pressure is lower downstream. But this expectation depends on the specific geometry. The actual crossing at 119 astronomical units is informative precisely because it constrains these geometric expectations with direct measurement. Let us now talk about the interstellar magnetic field specifically, about what Voyager 2's magnetometer has revealed about the magnetic structure of the local interstellar medium, and why this matters for understanding the heliosphere and its environment. The interstellar magnetic field is a fundamental property of the interstellar medium. It shapes the distribution of cosmic rays, influences the dynamics of interstellar clouds, and provides the medium through which energy is transmitted through the galaxy on large scales. But it is also very difficult to measure precisely. Indirect measurements through observations of polarized starlight, which is affected by the magnetic field along the line of sight, through measurements of synchrotron emission from relativistic electrons spiraling around field lines, give information about the field integrated along long paths through the interstellar medium. They cannot easily characterize the field locally. Direct measurements from a spacecraft in the interstellar medium, like those from Voyager 1 and Voyager 2's magnetometers, give the local field directly. These measurements are therefore unique data points in our understanding of the local interstellar magnetic field. The field measured by Voyager 1 outside the heliopause has a strength of approximately 0.4 to 0.5 nanotesla, extremely weak by everyday standards, but consistent with typical interstellar field strengths. The direction of the field, the orientation of the magnetic vector, points roughly in the direction expected from pre-mission models of the local interstellar field, based on indirect observations. Voyager 2's magnetometer outside the heliopause has confirmed the field strength and found a direction that is similar but not identical to Voyager 1's measurement. The difference in directions between the two measurements, from two spacecraft separated by roughly 30 to 40 astronomical units transverse to their separation in the radial direction, constrains the spatial coherence of the interstellar magnetic field on this scale. The field appears to be reasonably coherent, pointing in a similar direction at both measurement locations, suggesting that the scale of magnetic field variations in the local interstellar medium is larger than the separation between the two spacecraft. This coherence length of the interstellar magnetic field is relevant for understanding how cosmic rays propagate through the interstellar medium. Cosmic rays, high-energy charged particles, are deflected by magnetic fields. The larger the coherence length of the field, the more efficiently it can confine cosmic rays and prevent them from streaming freely through space. The Voyager measurements are beginning to constrain this coherence length directly from in situ measurements, rather than from indirect inferences. The specific alignment between the interstellar magnetic field direction and the direction of the local interstellar medium flow, the direction from which the medium is moving toward the Sun, is another quantity that can be constrained by combining the Voyager measurements with other observations. If the field is aligned with the flow, it suggests that the interstellar medium has been organized by the same process that sets the flow direction, perhaps the expansion of a supernova remnant that created the local bubble. If the field is significantly misaligned, it suggests a different history. Current data suggests that the interstellar field in our local region is roughly, but not precisely, aligned with the local interstellar medium flow. The implications of this alignment for the dynamics of the heliosphere, for the deflection of low-energy cosmic rays, for the structure of the heliospheric tail, are being worked out in ongoing theoretical and computational studies. All of this is being constrained by data from 2 spacecraft launched in 1977, with instruments designed for planetary science and adapted for interstellar work. The sensitivity and precision of the Voyager magnetometers in the interstellar regime is impressive but limited. Modern magnetometers would be significantly more capable. The interstellar probe concept specifically includes improved magnetometry as one of its key science capabilities. Let us now talk about the cosmic ray measurements from Voyager 2, about what the particle detectors aboard the spacecraft have found in interstellar space, and why these measurements are important for understanding the galaxy. Galactic cosmic rays, high-energy charged particles accelerated by supernova shock waves and other energetic processes in the galaxy, pervade the interstellar medium. They are present everywhere, but their flux inside the heliosphere is modulated by the solar wind and magnetic field. The heliosphere acts as a partial barrier that reduces the intensity of low-energy cosmic rays reaching the inner solar system. When Voyager 2 crossed the heliopause, its cosmic ray detectors recorded a dramatic increase in the flux of low-energy cosmic rays, exactly as expected if the heliosphere was shielding the inner solar system from these particles. The increase was approximately a factor of 2 to 3 for galactic cosmic rays in the energy range detected by Voyager's instruments. This confirmed that the heliosphere is indeed a significant shield against low-energy galactic cosmic rays. The specific energy spectrum of galactic cosmic rays in the interstellar medium, how many particles there are of each energy, is one of the fundamental measurements of cosmic ray physics. Before Voyager's crossing, the spectrum in the interstellar medium had to be inferred by correcting for the heliospheric modulation of the measured cosmic ray spectrum inside the heliosphere. This correction introduced significant uncertainties because the details of heliospheric modulation were not well known. Voyager's direct measurements outside the heliopause eliminate this uncertainty. They measure the actual interstellar cosmic ray spectrum without any heliospheric correction needed. The spectrum measured by Voyager 1 and confirmed by Voyager 2 shows a flattening at low energies relative to what models had predicted. The flux of low-energy cosmic rays is somewhat lower in the interstellar medium than extrapolations from inner heliosphere measurements suggested. This is unexpected, and its explanation is not fully settled. One possibility is that there are additional sources of cosmic ray modulation in the interstellar medium beyond the heliosphere. perhaps magnetic turbulence or other plasma processes that reduce the flux of low-energy particles. Another possibility is that the local interstellar medium in our immediate neighbourhood has specific properties that distinguish it from the average interstellar medium. Perhaps the local interstellar cloud has a somewhat lower cosmic ray flux than the typical interstellar environment. The cosmic ray measurements are also sensitive to the large-scale structure of the galactic magnetic field. Cosmic rays are deflected by magnetic fields. Low-energy particles are deflected more strongly than high-energy particles. The anisotropy of the cosmic ray flux, the directional dependence of how many particles arrive from which direction, carries information about the magnetic field structure that has deflected them on their journey from their sources. Voyager's cosmic ray detectors can measure this anisotropy, providing additional constraints on the local magnetic environment. Let us now talk about something more personal, about what it means for the people who built Voyager 2 and who have spent careers maintaining it to know that the mission is ending. Ed Stone, who served as the Voyager project scientist from 1972 until 2022, a span of 50 years that made him the longest-serving project scientist of any NASA mission, has described the experience of watching Voyager cross the heliopause as one of the most profound of his scientific career. He was there when the spacecraft were launched. He was there for the planetary flybys. He was there when Voyager 1 crossed the heliopause in 2012 and when Voyager 2 crossed in 2018. He watched as the instruments that he had worked for decades confirmed that the heliosphere has a definite boundary and that interstellar space has specific, measurable properties. He described the data coming back from the crossing as beautiful, not in a sentimental sense, but in the scientific sense of data that confirms and extends and complicates understanding simultaneously. Data that answers some questions definitively and opens new ones. Data that no model fully predicted and that therefore constrains models in ways that will advance understanding. The people who have worked on Voyager for decades carry a specific relationship to these spacecraft that is not easily replicated in any other context. They have watched the spacecraft move away from Earth for years, decades, lifetimes. They have made decisions about trajectories, about instrument operations, about power management that shaped what the spacecraft measured and what we learned. They know the spacecraft in the way that you know something you have worked with for a very long time, its specific quirks, its failure modes, its capabilities and limitations. When Voyager 2 goes silent, the people who know it best will experience something that is part professional completion and part personal loss. The completion of a half-century project, the end of something they gave enormous parts of their lives to. The knowledge that the spacecraft will continue moving, that in this specific sense it will never end, but that the conversation is over. This is a specific kind of ending that has no exact human analogue. The person who builds something and sends it away, knowing they will never see it again, knowing the object will outlive them, outlive their civilization, outlive everything they know, is in a strange relationship to what they have made. It is theirs in the sense that they built it and understood it and communicated with it for decades. It is not theirs in the sense that it belongs now to the interstellar void, to whatever future there is, known or unknown. The Golden Record is the most explicit expression of this specific relationship. The record says, "We built this thing and we sent it out and we know we will not get it back and we know almost certainly that no one will ever find it, and we put a message on it anyway. Because we wanted to say something. Because the act of saying something, even into a silence that is almost certain to be permanent, is itself meaningful." Let us now talk about what Voyager 2 means for the question of interstellar travel. Not the science fiction version of interstellar travel, not faster-than-light ships or wormholes, but the real physics of what it would actually take to send something to another star. Voyager 2 is the fastest object that humanity has ever launched on a trajectory away from the Sun. Or, more precisely, it was on a faster trajectory than objects launched before it, and it has been overtaken in speed only by Voyager 1, which received a more effective gravity assist from Saturn. At 15.4 kilometers per second, Voyager 2 would take approximately 73,000 years to travel the 4.24 light-years to Proxima Centauri, if it were heading in that direction, which it is not. 73,000 years is not a mission timescale that any reasonable planning horizon can accommodate. It is approximately equal to the time since modern human beings first arrived in Australia, a period encompassing essentially all of recorded history many times over. A mission launched today with Voyager-level propulsion that arrived at Proxima Centauri would arrive in a future so remote that the civilization that launched it would likely be unrecognizable or non-existent. Faster propulsion is therefore essential for any meaningful interstellar mission. The options that have been seriously studied include nuclear thermal propulsion, using nuclear reactors to heat propellant and expel it at higher velocities than chemical rockets, which could achieve exhaust velocities of approximately 8 to 9 kilometers per second, roughly doubling the specific impulse of chemical propulsion. Nuclear pulse propulsion, the Orion concept using nuclear explosions to propel a spacecraft, could achieve dramatically higher velocities but faces political and practical obstacles. More speculative proposals include laser sails, lightweight spacecraft pushed by powerful Earth-based lasers, which could, in principle, reach significant fractions of the speed of light, if the laser power and sail area are sufficient. The Breakthrough Starshot initiative, announced in 2016, proposed using a ground-based laser array to push gram-scale spacecraft to approximately 20% of the speed of light, reaching Proxima Centauri in approximately 20 years. The engineering challenges are formidable, and no such system has been built. But the concept is not obviously inconsistent with known physics. Fusion propulsion, using controlled nuclear fusion to generate propellant, could achieve exhaust velocities much higher than fission-based systems if controlled fusion can be achieved. The specific impulse achievable with fusion propulsion could potentially allow transit times to the nearest stars of centuries rather than millennia. Still a very long time, but within the range of what a deliberately planned multi-generational project might accomplish. All of these propulsion concepts remain far from implementation. The fastest spacecraft ever built, the Parker Solar Probe at its closest solar approach, reaches approximately 700,000 kilometers per hour, about 195 kilometers per second. But this is achieved by falling toward the Sun, not by propulsion power alone, and cannot be sustained for interstellar travel. Purpose-built interstellar propulsion has not yet been demonstrated at any scale. Voyager 2, therefore, represents, despite its extraordinary achievement, essentially the bottom of the realistic propulsion scale for interstellar travel. It is moving as fast as we could make it go, with 1970s propulsion technology and gravitational assists from the outer planets. It is so slow relative to interstellar distances that its transit time to the nearest stars would span civilizations. This context makes the achievement of Voyager 2 all the more extraordinary in one sense, and all the more humbling in another. Extraordinary because we actually sent it. We actually built a spacecraft and launched it and guided it past 4 planets and watched it cross into interstellar space and continue communicating for nearly 50 years. Humbling because what we built is so slow relative to what interstellar distances demand that the nearest stars remain effectively unreachable on any timescale relevant to human civilization as it currently exists. The stars are far. We are slow. Voyager 2 is the concrete expression of both facts simultaneously. Let us now talk about the specific measurements Voyager 2 has made in the heliosheath, the region between the termination shock and the heliopause, that revealed the complexity of this region and set the stage for the interstellar measurements that followed. Voyager 2 crossed the termination shock, the boundary where the supersonic solar wind slows to subsonic speeds, in August 2007 at approximately 84 astronomical units. The crossing was detected by all of Voyager 2's particle and field instruments and confirmed definitively that the termination shock is a real physical boundary where the solar wind decelerates sharply. After crossing the termination shock, Voyager 2 entered the heliosheath, the region of decelerated turbulent solar wind between the termination shock and the heliopause. It spent approximately 11 years in the heliosheath before crossing the heliopause in November 2018. The heliosheath turned out to be far more complex than pre-mission models had suggested. The solar wind in the heliosheath is turbulent and highly variable. Voyager 2 observed significant fluctuations in the plasma density, temperature, and magnetic field strength on timescales of days to weeks. The direction of the magnetic field in the heliosheath varies considerably, unlike the relatively ordered heliospheric magnetic field inside the termination shock. Voyager 2 also detected energetic neutral atoms, fast-moving neutral particles produced when energetic ions in the heliosheath charge exchange with neutral atoms drifting in from the interstellar medium. These particles are produced specifically at the heliospheric boundary, and their energy and direction of travel encode information about the plasma conditions in the heliosheath. The detection of these particles by Voyager 2 provided complementary data to the maps of the heliosphere produced by the IBEX spacecraft, which detect similar particles from Earth orbit. The heliosheath observations from Voyager 2 were scientifically rich, providing the first direct measurements of this region from the southern hemisphere of the heliosphere. But they also revealed how much more complex the heliospheric boundary region is than the models that existed before direct measurements. This complexity has motivated the development of more sophisticated numerical models of the heliosphere that include the effects of neutral interstellar atoms crossing the heliopause, the dynamics of the termination shock, and the turbulent structure of the heliosheath. The science of the heliosphere, of the Sun's influence on its surrounding environment and the boundary between that influence and the broader interstellar medium, is a field that has been fundamentally transformed by the Voyager data. Models that seemed adequate before the measurements turned out to be missing important physics. The real heliosphere is more complex, more variable, more structured than the pre-mission picture. This is precisely what direct measurement does that remote observation cannot. It finds the unexpected. It discovers that reality is more textured than the models predicted. It forces the models to improve. And in improving the models, it advances understanding not just of the specific system being measured, but of the broader class of phenomena, the heliospheres of other stars, the interaction of stellar winds with the interstellar medium throughout the galaxy, the cosmic ray environment experienced by potentially habitable planets around other stars. Let us now talk about the Oort cloud, the vast reservoir of comets that surrounds the solar system at enormous distances, and what Voyager 2's trajectory tells us about when the spacecraft will reach it and what that means for the boundary of the solar system. The Oort cloud is a hypothetical spherical shell of icy objects surrounding the Sun at distances of approximately 2,000 to 100,000 astronomical units, extending to roughly a light-year from the Sun at its outer edge. The existence of the Oort cloud is inferred from the orbits of long-period comets with orbital periods of hundreds to millions of years that arrive from all directions and from very large distances. The statistical distribution of these orbits is consistent with the comets being perturbed from a spherical cloud at large distances by the gravitational influence of passing stars and the tidal force of the Milky Way. Voyager 2 is currently at approximately 133 astronomical units, far beyond the outer planets, but only about 7% of the way to the inner edge of the Oort cloud, which begins at approximately 2,000 astronomical units. At its current speed of 3.2 astronomical units per year, Voyager 2 will take approximately 580 years to reach the inner edge of the Oort cloud. It will take approximately 29,000 years to travel through the Oort cloud to its outer edge. The Oort cloud is not dense enough to be a significant obstacle to Voyager 2's passage. The estimated number of Oort cloud objects is between 100 billion and 2 trillion, an enormous population, but spread over an enormous volume. The outer Oort cloud encompasses a volume approximately 10 million times larger than the volume of the inner solar system. The average density is extraordinarily low. The chance of Voyager 2 colliding with an Oort cloud object during its transit is negligibly small. But the Oort cloud is still technically part of the solar system. The objects in it are gravitationally bound to the Sun. Voyager 2's passage through the Oort cloud will take tens of thousands of years, and its instruments will long since have gone silent. By the time it reaches the inner Oort cloud, approximately 580 years from now, in the early 26th century, the instruments will have been silent for perhaps 500 years. The outer edge of the Oort cloud, at approximately 100,000 astronomical units, roughly 1.6 light-years from the Sun, is where the Sun's gravitational influence becomes comparable to the gravitational influence of the nearest stars. Beyond this boundary, objects are not stably bound to the Sun and can be pulled away by passing stars. This is the gravitational edge of the solar system, the most physically meaningful definition of where the solar system ends. Voyager 2 will cross this boundary in approximately 30,000 years. At that point, it will have definitively left the solar system, not just the heliosphere, not just the planetary system, but the gravitational domain of the Sun. The Sun will still be the brightest star in the sky from Voyager 2's perspective, but it will no longer be the dominant gravitational influence on the spacecraft's trajectory. The spacecraft will be fully in interstellar space in every meaningful physical sense. This moment, the final gravitational departure from the solar system, will occur in complete silence approximately 30,000 years from now. No one will observe it. No instrument will record it. Voyager 2 will cross this final threshold alone and dark and moving and carrying its message from 1977. Let us now talk about the stars that Voyager 2 will approach, not just Ross 248, which it will pass in 40,000 years, but the longer sequence of stellar encounters that will define its trajectory through the galaxy over longer timescales. After the Ross 248 encounter in approximately 40,000 years, the next close stellar encounter in Voyager 2's trajectory is not well determined because the accumulated gravitational perturbations from Ross 248 and other close approaches will have significantly modified the spacecraft's trajectory from what simple extrapolation of its current velocity would predict. The uncertainty in Voyager 2's position and velocity 40,000 years from now, given the uncertainties in the masses and positions of all stars it will pass near, is already significant. But statistical statements can be made. Based on the density of stars in the solar neighbourhood and the typical velocities of stellar encounters, Voyager 2 will pass within 1 light-year of a star approximately once every million years. Most of these encounters will be with red dwarf stars. M-type stars are by far the most common type in the galaxy, comprising approximately 70% of all stars. Red dwarfs are intrinsically faint. None is visible to the naked eye from Earth, but they are numerous enough that random stellar encounters are dominated by them statistically. Each close encounter will modify Voyager 2's trajectory through a gravitational perturbation, whose magnitude depends on the mass of the star and the closest approach distance. Over millions of years, these perturbations accumulate, and the trajectory becomes a random walk through the stellar population of the galaxy. After approximately 10 million years, the timescale on which gravitational chaos makes the trajectory unpredictable, Voyager 2's position and velocity are no longer deterministic from current knowledge. It could be anywhere within a large volume of the galaxy and heading in essentially any direction. Over billions of years, timescales comparable to the current age of the universe, Voyager 2 will execute a complex orbit through the Milky Way galaxy. It is moving at a velocity relative to the galactic center that is approximately equal to the typical velocity dispersion of stars in the galactic disk, meaning it is not on a dramatically unusual orbit that would quickly carry it out of the disk or into the galactic halo. It will remain approximately in the disk of the Milky Way for billions of years, orbiting the galactic center on an orbit modified by every stellar encounter along the way. In the far future, after the Milky Way and Andromeda merge, approximately 4.5 billion years from now, Voyager 2 will be part of the resulting merged galaxy. The merger will modify its orbit. The gravitational dynamics of two galaxies colliding will produce tidal streams and scattered populations of stars ejected to large radii. Voyager 2 may or may not be ejected from the merged galaxy, depending on specific orbital mechanics that cannot be predicted from current information. On timescales of trillions of years, stellar interactions will gradually strip stars from the merged galaxy. Voyager 2, caught in this process, may eventually be ejected into intergalactic space, traveling through the vast emptiness between galaxies. Or it may fall into the central supermassive black hole through a series of orbital interactions. Or it may simply continue orbiting, moving through an increasingly dark and depopulated galaxy as the stars burn out one by one. There is no final destination. There is no end point to this story. Voyager 2's journey, after the instruments go silent and the mission ends and the civilization that built it has transformed beyond recognition, will simply continue. Through the interstellar medium, past occasional stars, through the evolving galaxy, for as long as the physical laws that govern its motion continue to apply, and as long as something remains to move through. The universe is patient. It does not require the journey to end. It does not require a destination. It simply continues. And Voyager 2, small, silent, gold-plated record and all, continues with it. Let us now talk about the specific content of Voyager 2's Golden Record in more detail, about what was chosen, how it was chosen, and what the specific selection tells us about the people who made it. The process of assembling the Golden Record was described by Carl Sagan and others involved as one of the most challenging curatorial exercises any of them had attempted. The task was to represent all of humanity, all of its music, its languages, its visual art, its natural sounds, its science, in a record that could fit on a 12-inch disc and that could be understood by a receiver with no knowledge of Earth or its languages. The images on the record were encoded as analog video signals, a format chosen because it does not require any specific decoding technology beyond the ability to interpret a time-varying signal as a spatial pattern. The first images on the record are calibration images, a circle, mathematical symbols that allow a finder to verify they have decoded the format correctly before attempting more complex images. The sequence of images progresses from mathematical and scientific concepts, atomic structure, the solar system, Earth from space, through biological illustrations, DNA structure, human anatomy, conception and birth, to human life and culture, people of diverse ethnicities, families, cities, architecture, food preparation, sports, and finally to scientific instruments and the spacecraft itself. The sequence was designed to build from the universal, mathematics and physics, toward the specific, human culture, in a way that a sufficiently advanced receiver might follow. The music selection was assembled by a committee that included ethnomusicologist Alan Lomax, who had spent decades recording folk music from around the world. The selection spans 90 minutes and includes works from approximately 28 countries and traditions. The decision to include Louis Armstrong's Melancholy Blues alongside Bach's Brandenburg Concerto, alongside traditional music from Senegal and Georgia and Azerbaijan and Peru and Australia, reflects a genuine effort to represent the diversity of human musical expression. The decision to include Chuck Berry's Johnny B. Goode was controversial within the committee. Some members felt it was too popular, too commercial, insufficiently representative of the best of human music. Carl Sagan reportedly responded that teenagers exist in space too, a defense of inclusive representation over elite selectivity. Berry himself, when told about the inclusion, reportedly said, "Roll over, Beethoven, and tell Tchaikovsky the news," an apt response. The spoken greetings in 55 languages begin with Akkadian, the language of ancient Mesopotamia, now dead for more than 2,000 years, and proceed through the major world languages to several hundred speaker languages that might not survive to the record's potential recovery. The final greeting was recorded by a child, Nick Sagan, Carl Sagan's 6-year-old son, who said in English, "Hello from the children of planet Earth." Hello from the children of planet Earth. Recorded in 1977 by a 6-year-old boy, now on a spacecraft in interstellar space, moving through the void at 15.4 kilometers per second, carrying this greeting into a silence that will almost certainly never be broken by any listener. Nick Sagan grew up to become a television writer and producer. Carl Sagan died in 1996 at the age of 62, before Voyager 2 crossed the heliopause, before any of the interstellar science was done. He never knew what the spacecraft he helped send found in interstellar space. The record remains. The message remains. The journey continues. The final place Voyager 2 will reach before it dies, before its instruments go silent and its signal ceases and the mission formally ends, is simply wherever it is when the power finally fails. Not a named destination, not a specific astronomical feature, just a point in the interstellar medium at some distance from the Sun in the direction of telescopium. A point that will have no significance except that it is where the conversation ended. But after that point, everything continues. The spacecraft continues, the record continues, the message continues, and the journey that will outlast everything that sent it, never reaches a final place at all. There is a specific calculation you can do right now. Voyager 2 is approximately 133 astronomical units from the Sun. It is moving at 15.4 kilometers per second. It has been traveling since August 20th, 1977. 47 years. In the time it takes you to read this sentence, it will have moved another several hundred kilometers from the point where it was when you started reading. It is out there right now. Not metaphorically, physically, a real object, 733 kilograms of metal and electronics and one gold-plated copper disc, moving through the interstellar medium at 15.4 kilometers per second. Its plasma wave instrument is measuring the density of the electrons in the local interstellar cloud. Its magnetometer is measuring the direction and intensity of the interstellar magnetic field. Its cosmic ray detectors are counting high-energy particles that were accelerated by supernova explosions somewhere in the galaxy. Particles that have been traveling for thousands of years before arriving at the precise location of Voyager 2 at this precise moment and being counted. All of this is happening right now. And all of it is being transmitted back to Earth at 160 bits per second, the speed of a 1970s modem, on a signal of 23 watts, crossing 20 billion kilometers of space, arriving at the 70-meter dishes of the Deep Space Network with a power of approximately 10 to the negative 16 watts. Less power than it takes to illuminate a single pixel on the screen you might be reading this on. Received, decoded, turned into data. Analyzed by scientists who understand they are working with something irreplaceable and finite. The signal will stop. Not today, probably not this year, but within years, not decades, the last instrument will fall silent, and then the transmitter will fall silent, and the conversation that has been ongoing for nearly half a century will end. The Deep Space Network antennas will point in the direction of Voyager 2 and receive nothing except the noise floor of the receivers. After verification, the mission will be declared over. After that, Voyager 2 will do something that almost nothing humanity has ever built can do. It will continue. It will continue through the local interstellar cloud, the warm, partially ionized gas that our solar system is currently moving through, for thousands of years. It will pass within 1.7 light-years of Ross 248, approximately 40,000 years from now, the closest it will come to any known star in its foreseeable trajectory. The encounter will perturb its trajectory slightly, and it will continue. It will pass through the inner edge of the Oort cloud approximately 580 years from now, while its instruments are already long silent. It will travel through the Oort cloud, the vast reservoir of distant comets that represents the gravitational edge of the solar system, for approximately 29,000 years. It will cross the gravitational boundary of the solar system, the point at which the Sun's gravity ceases to be the dominant influence, approximately 30,000 years from now. At that point, Voyager 2 will have definitively left the solar system in every physical sense. No instruments will record this moment, no signal will be sent, no observation will be made. The crossing will happen in complete silence, in a spacecraft that has been dark for approximately 27,000 years. And it will continue. The stars it will pass over the next millions of years are unknown. The gravitational perturbations from early encounters will make its trajectory unpredictable on those timescales. But statistically, it will pass within a light year of a star approximately once per million years. Each encounter will slightly modify its trajectory. Over billions of years, those modifications will accumulate into something that no equation we write today can predict. It will be in the galaxy when the Milky Way and Andromeda merge 4.5 billion years from now. The merger will modify the orbits of hundreds of billions of stars, and through the gravitational dynamics of that merger, Voyager 2's trajectory will be modified too. It may be ejected into intergalactic space. It may remain in the merged galaxy. The specific outcome is not predictable. What is predictable, with certainty, is that it will continue moving through whatever space it finds itself in. No friction, no drag, no mechanism to stop it. The momentum it has had since the gravity assist from Neptune in 1989 will persist essentially forever. The laws of physics do not have an expiration date. The golden record will be there, still attached. The gold plating protecting the copper beneath from cosmic ray bombardment. The sounds of Earth encoded in the analog grooves, the waves breaking on a shore, the wind, the thunder, the first cries of a newborn child, the music of a dozen cultures, the voice of a 6-year-old boy saying hello from the children of planet Earth. Those sounds were recorded in 1977. The people who made them, Carl Sagan, who conceived the record, Anne Druyan, who curated the music, the engineers who built the spacecraft, the scientists who planned the trajectory, most of them are no longer alive. The child whose voice is the last greeting on the record is now in his mid-50s. The civilization that built the spacecraft has changed in ways that 1977 could not have anticipated, and will change further in ways that we cannot anticipate now. But the record moved through space at 15.4 kilometers per second, unconcerned with any of this, indifferent to the passing of generations and civilizations, subject only to the laws of physics which apply equally to grains of interstellar dust and to spacecraft carrying golden records, and to the stars themselves. There is something specific that this calls for, not sentimentality, not false comfort, not the pretense that the record will be found or that the message will be received. The probability that any civilization will ever find Voyager 2 is, for practical purposes, 0. The record will almost certainly travel forever without being played. The message will almost certainly be sent into a silence that is never broken. But the record was not made for its receiver. It was made for its sender. The act of assembling those sounds and images, of deciding that this is what we want to say about ourselves, this is what we believe represents us, this is what we think is worth carrying into the cosmos, was an act of self-definition by a civilization at a specific moment in its history. The record is humanity looking at itself and choosing what to show, and sending it out anyway, into a silence almost certainly permanent. At 15.4 kilometers per second, away from the only home it has ever known, this is what the Voyager mission ultimately is. Not a scientific mission, though the science is extraordinary, transformative, irreplaceable. Not a technological achievement, there the engineering is among the most remarkable ever accomplished, but an act of presence in the universe, a statement that we were here, that we existed, that we looked outward and wondered and built something and sent it. The universe will not notice. The stars will not care. Ross 248 will not pause in its motion across the galaxy as Voyager 2 drifts past in 40,000 years. The interstellar medium will not record the passage. The silence through which the spacecraft travels will not be interrupted by any acknowledgement of what is moving through it. But it is there, right now, moving through that silence at 15.4 kilometers per second, measuring the interstellar medium for the last few years before it goes dark, carrying its record, moving toward a future it will never know, and but we will never see. The final place Voyager 2 will reach before it dies is not a place you can point to on a map. It is wherever the last photon of its transmitter reaches the last receiver still listening, somewhere in the interstellar medium, at some distance from the Sun that will be slightly larger than the current 133 astronomical units, at some time in the next several years. After that, not death in any complete sense, silence, and then eternal motion. The spacecraft will continue, the record will continue, the message will continue, into the dark. At 15.4 kilometers per second, forever.